For this, what we are going to do is, I hope all of you are familiar with what's a sine waveform is. It's the output of a trigonometric function called sine. So it oscillates between +1 and -1, right, and have characteristics like this one user thing. So there are very efficient and fast algorithms that can generate sine waveforms that all you should be using if you ever got a requirement to use a sine waveform. But this is done as an example, and since it needs only one input and one output, it's very easy for a starting person to learn from this point. That's why we chose this, and that's why the authors of the book have chosen it. So what we are going to do is, first we'll generate a sine waveform from a optimized and proven algorithm, like the one in Python math library. Then we'll sample that sine wave from random points and get the values of those. Then we'll train a simple like 3-layer neural network with fully connected layers. This is a very simple regression problem. I hope you all are familiar with what regression is by now. Then we'll evaluate it to see the correct values are coming, and it has trained the correct or the approximately correct characteristics. Like in this kind of approach, we cannot expect a neural network to perform as accurate as the exact sine function, but goes close with it. That would be fine for us. Like if it can match the shape, that would be fine for us. And at the last stage, we will convert that model to TensorFlow Lite format and see how we can put it inside the microcontroller. So our end goal of this application would be to see how a waveform like this can be created with this neural network on the STM32 F7 nuclear board, which I'm going to use for this tutorial. Right. So let's see how we can do this. Unmute and ask, or you can put them in the chat during this session. I'll try my best to answer and help you out. So our first step would be to create an Google Colab notebook. And we need few Python libraries like TensorFlow, NumPy, Matplotlib for the plotting, math, and layers from the Keras. Those will be our dependencies. So we can check what's the TensorFlow version they have included. Actually, we don't need to do this. Like now the Colab use TensorFlow 2 as default, so there's no need to do it, but just to check. Here I'll be setting up few variables that will be useful for us. So the number of samples would be the number of points that we are going to sample from the original or the correct sine wave. Unlike in normal AI applications, we won't be using any dataset captured or recorded from outside. For this example, we'll be generating a simple dataset. then validation ratio and test ratio. I hope you will be aware of what these things are. Like we need to split the data set into 3 sets, like training set, validation test set, and the test set. So these will be the percentages that we're going to split them. Okay, let's go. So here I'm generating an NumPy array with random values between 0 and 25. So 25 is the radian value for and complete angle, like 360 degrees. For this application, we are using radians instead of degrees. So its radians is simply another unit used to measure the angles. So sine, we can generate a sine waveform simply with a sine array of values, simply with those values using NumPy sine method. Let's see how the values are spread. So here we can see a nice sine waveform is generated from 0 to +1 and -1. Then we'll add some noise to this. Like the reason is that we won't be able to properly train a data set without some randomness of this nature. Otherwise the data set, otherwise the network will overfit to the training data. That's why we are adding some randomness. So if we add, so there's a small mistake. Okay, so here I have added some noise, but it's too much, so we cannot see the actual waveform from it. So I'm going to multiply it by my 0.1 and see the output. So we'll have a nice sine shape with this, with some noise. Next, we'll split the data set into 3 categories: validation, test, and train. So this can be done with NumPy split method. All we need to give it is the ratios we need to split the array. With that, we'll have X validation, X test, and X train arrays for the input data, and therefore the expected outputs we have Y value, Y test, and Y train. In order to see that we have split the original data set correctly without losing any data, we can use an assertion. What this assertion does is it will just add all these 3 values and see if the count is equal to the entire number of samples, which we decided as 1000. So if we run it, there won't be an error if the count is different. Just to see how an assertion works, we'll have an error. Okay, moving forward, let's see how this data has spread around spread in our main data set. So let's plot it with 3 colors. And here you can see it has spread evenly, like blue ones are the values in the training set, red ones are in the test set, and in the validation set values are marked in yellow. Let's create our neural network model using here sequential. So the first layer would be have a width of 16 neurons at activation ReLU, and our input would be a single value, so the input shape would be 1. The next layer would also be a 16 neural network 1 with the activation value. And the output would be a neural network that comes from 16 to 1, since we only need one value as the output. So 16 into 1 would be the correct size for the output layer. So as in summary, we can see the first layer is 16, the next one is also 16. We are doing this with all fully connected layers, since this is a very simple application. We'll use the RMS prop as our optimization and the mean absolute error as the loss. Like these values are change between minus and plus values, and just having the difference between the correct value and the value we are given from the network would be enough to have a proper measurement on the accuracy. So the mean absolute error would be enough for this application. So let's train this model with 600 epochs and batch size of 16 and see how it behaves. So here I'm starting the training. It takes quite few minutes to complete the training. So I'll fast forward. So the training has completed. So if we plot the history, we can see how the training and validation losses have evolved through the training process. We are just simply getting those from the history and plotting them with the number of epochs we ran through. So here we can see the loss function, how the loss function has behaved, and it has gone down with time. So let's run inference on the trained model and see how it works. So we'll use the test for that. So here I have done a mistake again with the plot function. Heading2.c has fixed it. So here we can see in red how the predictions have gone through. It has followed a sine waveform, but it hasn't followed a pure sine waveform. It has few rough edges, but it's okay. Like we only need to see how well it follows the shape of a sine. Okay, so that's it. I hope it's very clear how the sine waveform is created. Okay. The next step would be to convert this to a file format that we can put inside the microcontroller, or also by optimizing the neural network. There's one question asked, what is meant by inference? So running inference means the same thing like running a program we written. But here in ML domain, we have two things to do. Like first, we need to train our neural network or our deep learning model. Then we have to give inputs to it and check the output. Like this is not for the validation only. When we are using this, we need to give it inputs and see the output. So running inference means that supplying inputs to the model we trained, then getting the output. So it's somewhat same as running our model, but the correct term is running inference in uh, AI domain. I hope it's clear. So here there's nothing much to explain, like this is the same functions we need to use that is explained in the TF library. All it does is it needs the model and the amount of optimization. Then it will generate a file for us that we can use in our next step. So after the file is generated, all we need to do is simply download that file. Okay, I'll show you how the download is done. In our file in here, we'll have the file section, and when we complete the run, I'll just run it here and show you in a later moment how to download it. It's just right clicking and downloading the file. Okay. So I think you'll got the idea how to generate a sine wave from using a neural network. So the next step is to run it on STM32 microcontroller. So if we go to making a new project in STM32, okay. Okay, let's see how it's done. Right here. There's in the MCU selection sector, there's a special category called artificial intelligence. If we enable that radio button, we'll be able to sort out the chips that only supports artificial intelligence. But since I'm using a board, I'm just going with board selector. But that's a point you should keep in mind if you are going to use, if you are going to select a microcontroller in future and don't know what's the exact category you need to choose from. Okay, the setup would be as same as the previous steps. We need to make a new project and select our board or the microcontroller. Then configure the peripherals we need. But first we need to add the Cube AI support. So Cube AI is the library of artificial intelligence support that STM have given. So in the select components here, we need to just tick the Cube AI core and get the device application mode as the application template, like we are going to develop an application with this. All these will be automatically downloaded when you select this so there's nothing more to configure. Everything will be automatically downloaded into your PC and set up. Okay. So after that, we'll clear the pinouts since we are going to set them from the beginning. Okay, for this application, only thing we need is the UART. Like what I'm going to do is I'll give an input to the model with some array and get the output value from the UART as a serial print. So I'll select the correct pins for the UART that is connected through the USB port to my PC. Okay, next I need to enable the AI package. So here in software packs, there's this Xcube AI. And with it, using add network, I can simply select TF Lite. Like previously, we choose TF Lite as the file format. Then go to the downloads and select the correct file. Okay, that's it. Here they have given few features like we can compress our model. What compression does is it will shrink the precision of the weights in our model. Like if the weights are in 32-bit floats, then it one compression stage, it will convert them into integers. But if we need more compression, it will change them into 16-bit integers. Likewise, with compression, we'll lose some accuracy, but we'll be saving space for but these things are needed for very large models. But our model is very simple at this stage. We are not going to use any of them. Also, they have given a feature to add external RAM or external flashes when we need more memory to run our systems. So all those support are already in there. The next step would be to analyze the network. So to see that this program has the ability to get it identified and there's no problems or issues with it. I fast forward this. So after that, it has detected two dense layers and an input layer as we expected. Okay. It has given how much flash and the RAM that would be needed if we are using this model in our chip. So with these tools, you can actually see the chips before you purchase them, that they will have the ability to run your models. So these are very, very helpful tools. It also gives the ability to visualize the model, how the layers and how much complexity is there. That's basically it about setting up the peripherals. Then next we'll see the clock setup. We are only going to use the internal clock, and 16 megahertz is more than enough for our task. Then we'll let the tool to generate the code configurations. Right. So the next step would be to set up or configure the inputs and outputs to the model we created. So the model is already embedded into our firmware of the project right now. And they have given few APIs that we should use to interact with our model. And there are some special data types which we should use for our interfacing with our model. So here you can see in Xcube AI app directory, the files for our model has been created. So Sine model C, Sine model H, and you can see how the data and parameters are categorized in very methodical way in those files. So if you do this, you can go to those files and see what have been included in them. So the first step would be to include few headers that are needed for our task. The most important ones that are related to our model will be Sine model H and Sine model data.h. The reasons and why we need to include them are explained in the STM32 Cube AI manual in detail. But what you should take from this session is like basically get the idea what's happening here. You don't need to know these syntaxes by memory. The reason is that these workarounds change a lot. Like in their next QBI update, some methods and some procedures we used here will definitely will change. So the hardest thing about this Edge AI domain is the libraries change with each update, and old reference material and tutorials get outdated very quickly. So only thing you need to grasp in here is the workflow, not how the coding is done. I hope it's clear. So here I found out this approach by reading their source material or the reference manuals. So I will share those links with you, and whenever you are trying or making use of these libraries and of these tools, before starting, you must read their manuals and see how or what are the suggested methods they are giving to implement a neural network on their chips. So at this stage, at this time, the most updated QBI library has given this approach, like we need to have input and output data structures like this, and we can get the sizes, like input sizes and output sizes from these variables, and make them. So the next step would be to initialize our model in our main loop. But before that, I'm going to make a buffer, like 8-bit buffer, 8-bit long values buffer to get some serial data in Word format, so that I can see or develop a small application to see how each of these steps works inside the MCU. So these two variables are just for that, for the serial communication. After all the initializations happen, we can print something like this XQBI test and transmit it through the UART transmit mode. So we discussed about UART transmit in detail last week, and here we are just using the poly mode, like we are not expecting anything to done with higher efficiency here. Right, let's test this. Another thing to keep in mind is like instead of implementing everything and building it afterwards, it's little bit better to debug if we compile them at step by step while development. That way we can fix the issues at earliest possible. So when we run this, we should only get that sentence we type as the serial. So in here you can see in the terminal we are getting that. So that part is okay. The reason why I did this to see if there's an error happening in the initialization functions. Sometimes it's possible that these functions might go into error state if we did not properly do do the configurations. So if we violate something in our previous step by setting up the configurations using the GUI tool, we won't be able to get our code past these initialization steps. So we don't have that kind of an issue here. So the next step would be to initialize the model. So it's done as this. We will get an array for to keep the activations. So all I have done here are according to the reference manuals they have provided, that they have said you need these kind of steps before you going to initialize the model, and you need these kinds of variables or pointers to work it. So I made the necessary pointers and variables. Okay. Okay, after making then I also do a check that to make sure that I haven't done any mistakes in them. So there seems that there's none. So let's continue. So in here, I'm creating the network AI Sine model create and initialize method. So these methods are automatically generated for us from the configuration tool. So all we need to do is use them and call them properly. And to see if that step has generated an error or it has executed properly, we can use another step. Of course, we can do all these steps using the debug, but for illustration purposes, I'm trying to write everything in the serial port so you can better understand. So if it returns an error from this step, we can see that it has gone to an error state. Else, we can say it doesn't have gone to an error state. Okay, let's run it. Okay, here we can see that no instance created successfully. So we are not going to an error state, right? The initialization is okay. Next would be to get a report from the model that we have created. With this report, our program has the ability to check the model for its input and output sizes. So that's really helpful for our later stages. In here, I'm checking just that the report was successfully made, just to make sure that everything works properly. That's all. Okay, let's check it. And that runs directly right here. Right. So we did not go into an error state. Right. Okay. Let's have an input and output configured. So it's little bit going like rounds in setting up inputs and outputs, but we have to follow this proper way to do it. Okay, we'll assign those two locations to our pointers, like input and output. So those two pointers have the locations for which the input and output reports have come. Okay. Then we'll use that AI handle PTR. So it basically what it does is it handles the pointers in AI type. So those gets assigned like that. So the AI input and AI output will have the input and outputs for our model. Okay. So that's basically it. Then let's have an variable or the input that we need to use as an input. So I'm using a normal float variable called x, which has the value 1.5. So this 1.5 is not in degrees, but in radians. We should keep that in mind. So the first thing would be to convert this float value to an AI float that supports our input size. So that's the only hard thing we need to configure. Like we need to properly initialize our models and properly give them the correct variable sizes for their inputs and outputs. That's the only hard thing here. We need to do all the other things are handled by the tool. So if you know what type of an input and what type of an output we need to provide, then we can make the model without any problem. So the file type conversion, I'm using an for loop. This is also an suggestion from the reference. Like in here, our variable size is just one. Like our input would be an size 1. But if we have many input variables like more than 1, we might be needing to use this kind of an approach. But in order to show you that approach, I'm just doing that. But this can be done with single step at this step. So only thing here we are done is like we are casting the float to an AI float type. That's all. Right. So in here you can see AI model in one size is just one. So this loop only run once. Okay. Next step would be to run it with the variable input. So here I'm passing the address of the first value of the input array and the output array's first value to the AI Sine model run. And if the running has happened successfully, I'm also putting or printing a message like it has run without an issue or not. Like if in batch is 1, then it has run correctly. If else, it hasn't run correctly. And the next step would be to convert the AI float value to normal float so we can see it. It's done like this by typecasting the other way. So now I think you can see even there's a lot of code here, nothing much has done. Just converting variable types and assigning an initialization. Then okay, now we can run it. Here I have put it into debug mode, so we'll be uploading the code to the microcontroller, and in the debug we'll be able to see what's the value of y. Here we learned about how to use the debugging tool last week. So when I run it, we get 0.97777 value for y. This is much closer value, like the correct value we can get for radian 1.5 is around 0.974, but this is pretty close. Okay, so there's nothing much to be illustrated with this approach. So let's try to get it run continuously and plot the waveform from this. So I'll do some changes here to run it from 0 to 2.5. So 2.5 is like 2 times the value of 5, like 2 into 3.14. That's 6.28. So let's increment our value from 0 to 6.3 in steps of 0.1. Okay, so for that we'll be needing to run a flow loop from 0 to like 6.28, but we cannot do this with a for loop. So what I'm going to do is I'll have a variable like I or x here, and increment it up to 63 and increment the value like this, like 0.1. So we'll be incrementing our value from 0.1 and getting the maximum value x will get is 6.3. So that's enough, and our model is only trained to capture values between 0 to 6.28. So this would be fine. It only goes up to 6.2, so that's fine. Okay, so all the other things would be the same, like only we are incrementing our input and getting an output like the y value, which we saw previously, and only the value of the y will be transmitted using the UR. And just to have a small delay there. And here we get an warning with printf, like it cannot transmit floating points, so we need to initialize that that setting. So it's in their CC++ bit settings, MCU tool settings, and we need to put that tick for uprint float. That's it. So now the float can be sent. Let's run it. So we can see the values are coming with the serial terminal, but we cannot get an exact idea like what these values mean. So let's plot it and see what kind of a shape it is making. So for that, they have a nice tool called serial plotter in Arduino. So with that, as you can see, the nice sine waveform we are getting. And it also has that small rough edges we saw in the, so after the training of that neural network. So the neural network has been implemented successfully in our microcontroller now. So one simple thing we can do is to remove this. This function is made for the application development using another approach that is given from ST. Today I didn't use that approach, so I removed it. But if you like, you can learn more about that approach and implement that in your code. The thing with that approach would be it needs some editing in other files that are automatically generated instead on the files like main and the custom files. So that's a little bit harder to maintain such code. So that's why I suggested this approach. So here I am running the code continuously. You can see it generates somewhat nice sine waveform with same rough edges it had. Okay. So that's how we can use STM32 Cube IDE and Xcube AI to run a neural network on STM32 chip. It's quite useful tool that if we can use it,